Okay, hello and welcome back everybody. So I want to remind you where we were. We were really in this section, which was the common rules of the discrete derivative or the finite difference. And we had covered our first rule for finite differences, which was the product rule. And it behaved very similar to the product rule for continuous derivatives. We had the derivative of the first term times the second, plus the first term times the derivative of the second. But as opposed to the continuous derivatives, we did have to pay this extra price, which was really the derivative of both terms multiplied together. So that's what the product rule looks like. And we didn't get quite to this part, but I do have an example of the product rule being applied. Now keep in mind, as I've said before, you don't really ever have to use these rules for finite differences. It's not like in the continuous case where the rules are there to make computing the limits easier, because limits are hard to compute by themselves. In this case, the finite difference is actually quite easy to compute by itself. But let's actually go through it. This is just going to kind of reinforce our idea of using rules in a calculus context. So actually by applying these rules in a finite difference setting, you are actually training the same sort of skills that you would use if you're applying the rules of the continuous calculus. So it's good practice, even if maybe it's not the most useful thing in the world. Let's do it. We're going to do it with the product n squared and log of 2n. And in this case, if we already know that the finite difference of n squared happens to be 2n plus 1, maybe we also know that the finite difference of log of 2n happens to be log of 1 plus 1 over n, well, then we can apply the product rule for finite differences to their product, and we just write it out as, difference of a times b plus a times difference of b, and then plus the two differences multiplied together. And so what do I have? Well, I look at the difference of a, that happens to be 2n plus 1, so I include it. I look at b, that happens to be log of 2n, so I include it. I look at a, which happens to be n squared, so I include it, and I look at the difference of b, which happens to be log of 1 plus 1 over n, and so I include it, and then finally we're left with the difference of both of them multiplied together, and let's recall the difference of a is 2n plus 1, and the difference of b is log 1 plus 1 over n, so I include that as well. This is very similar to the product rule for the continuous derivative, but we just are applying a slightly different rule, and we have the one extra term we have to account for. We do actually have a quotient rule for finite differences. So even though I said at the beginning that you can kind of extract the quotient rule, at least in the continuous case from the chain rule and the power rule and the product rule, it'll turn out we don't have a very good chain rule for finite differences. So the fact that we can actually construct a quotient rule will kind of be its own special rule. It won't be a result of the chain rule anymore. What does a quotient rule actually look like for finite differences? Well, here it is. If we take the finite difference of a quotient, which I have here, it's going to be very similar. Once again, these are all going to act quite similarly to the continuous derivatives. And let's recall the continuous derivative quotient rule just over on the side here so that we can compare them correctly. d dx of the ratio f over g, well, this happens to be, in my mind, I think, bottom, d top, d meaning derivative, d top, minus top, d bottom, all over the bottom squared. And now let's look at what we have in finite differences. We have the bottom, d top, or that's my difference of the top, minus the top, d bottom. So far, everything has behaved the exact same as for the continuous derivative. And it's really close to the bottom squared in the denominator, right? It's bn plus 1 times bn. So it's a shift by 1 on one of the bottom terms. You could imagine if that shift weren't there, it would actually be the bottom squared. And so that's how close we actually get to the continuous derivative quotient rule. It's really, really close, but that bottom, we have a single shift. I do think it's a little bit useful to see where this comes from. We're kind of thinking, like before, can we force the finite difference to show up in the computation of the difference of a quotient? And so by definition, the difference of a quotient, we're just going to add 1 to both terms, and then we're going to subtract the ratio of the terms without adding 1 to their index. And if we want to combine fractions, same as always, we need to use a common denominator. And the way to find a common denominator, you're always going to look at the multiplication of the two denominators. So in this case, we're going to think about the common denominator being bn plus 1 times bn. And we can kind of already see where that's going to come from in our final answer. So that's a common denominator. And then what's the price we pay for having that denominator in the first case? Well, it's missing bn, so I'm going to include a bn in the numerator. And in the second case, the denominator is missing bn plus 1, so I'm going to go ahead and include that in the numerator. At this point, because everything's common, I can actually add, or in this case, subtract the numerators from each other and combine the denominators. So I'm left with the following in the numerator. And just like with the product rule, we can force this finite difference, maybe of an and the finite difference of bn, to show up. And what does the finite difference of an look like? Well, that's an plus 1 minus an, and the finite difference of bn is bn plus 1 minus bn. So we can go ahead and force those to show up. How do we do that? We've got an an plus 1 here, which is just like that term in the finite difference for an. But what are we missing? We're missing the minus an term. What do we do is we actually rearrange this term. We're going to grab this minus an on the right-hand side of that term. We're just going to pull it over to the left-hand side, which says that an plus 1 is actually equal to delta an plus an. And so what I'm actually going to do is I'm going to replace an plus 1 with delta an plus an. I'm going to do the same thing with this bn plus 1 over here. I'm going to replace it with delta bn plus bn. And then if I go ahead and distribute the bn to both terms on the left case and the an to both terms on the right, turns out there's going to be a few terms which cancel each other, and what I'm left with is exactly what I had claimed I was going to have, which is really the quotient rule we all know and love, but this very slightly shifted denominator. So let's go through an example of actually calculating that. We're going to use the same two functions we had before, or the same two sequences, n squared and log of 2n, but now we're just going to take the ratio of those two instead. And we're just going to write down the quotient rule, right? I mean, in this class, we've got these tables that are available to us. You'll see a similar table at the end of this section, which includes all of the common rules. So as long as you've got the table available to you, as long as you can recognize that, yeah, we've got a ratio of n squared divided by log of 2n. That's a little typo there. That should be a dividing sign. So we have delta of an divided by bn. Well, what is its rule? It has to be bn times delta an minus an times delta bn all over bn plus 1 times b. And so we just identify each of those terms in the rule. Bn is identified as log 2n, so I include log 2n. Delta an is identified as 2n plus 1, so we have 2n plus 1. An is identified as n squared, so we have n squared. And delta bn is identified as log 1 plus 1 over n, so we include log 1 plus 1 over n. And then the denominator maybe is a little bit special. We've got bn plus 1 here. What does it mean to have bn plus 1? Well, I'm just replacing every n, which happens to be inside of bn, right? Which normally there would just be an n here, but I'm replacing that n, the entire term, with an n plus 1. So I go ahead and shove n plus 1 in there. So I have log of 2, n plus 1, and then multiplied by bn, which is log of 2n. If I want to simplify that a little bit, I can, but in reality, not too much in this case ends up simplifying. That tends to be the case with the quotient rule for derivatives as well, where not too much tends to simplify. I do have a nice paragraph where I say the next relevant rule would probably be the chain rule. That's kind of the one you want to learn. It's really, really horrendous for finite differences. I'm going to click on this appendix real quick and send us there because I do have an appendix in this section that includes the chain rule. But just to give you an idea, this is what it looks like. And to a certain extent, I haven't actually taught some of this notation yet. This is notation we'll see very, very soon. But you can already tell just how horrendous this chain rule looks. And so for all intents and purposes, we're not going to cover it here. But I do want to show that it's technically something you can develop. There is, however, kind of a single consequence of the chain rule. You could interpret it like that. You could also interpret it as a statement in and of its own right. And that's that if I decide to take a sequence and shift it, and what do I mean by shifting? Well, I've taken the regular n, which is the subscript of a sequence, but I've shifted it or modified it by subtracting k from that subscript. You can imagine something like if an is n squared, then a n minus 2 happens to be n minus 2 squared, and so on. Well, if I go ahead and compute the finite difference of a shift, it actually doesn't change what the finite difference looks like. And so what I'm referring to on the right-hand side here is I can compute the finite difference as though there were no shift. That's why I've put parentheses around that specific term here, parentheses around delta a first, and then I've got this subscript here that basically says, and then perform a shift. What this means at the end of the day is we eventually have this table that combines all the rules, so like power rule, exponential rule, etc. You can think about something like n minus 2 to a specific power, maybe n minus 2 cubed. That would behave, I'll put an approximation symbol here. It basically behaves like n cubed up to the finite derivative, but then whatever your finite difference gives you, you then shift that by your negative 2 that's sitting there. So we'll see this in action later. It's just kind of a nice little thing to keep in mind that shifting my index is not going to change the finite difference aside from the fact that the output will also have a shifted index, but the overall behavior of the difference stays the same. Proof is really one line. It goes real quick. So you can just calculate this directly. Finite difference of a shifted sequence, well, finite difference is defined by taking n and adding 1 to it and then subtracting n without a plus 1 on it. The negative k's come along for the ride. And then if I simply kind of regroup this subscript into n minus k, group those terms together and then group the n minus k terms in the second subscript, well, what do we have? We have the entire n minus k term has been added 1, and then I've subtracted the entire n minus k term. Well, that's a definition of me actually computing delta a and then just evaluating that on n minus k. So these are one and the same thing. Let's see how this actually works in an example. It's going to make a little bit more sense. It's just like, suppose that I've got some sequence here. In this case, my sequence is n times n minus 1 times n minus 2. Suppose for some reason somebody's told me what this is, the finite difference that this sequence is equal to. They've told me that finite difference is 3 times n minus 1. I can go ahead and use the knowledge of this sequence and its finite difference to actually calculate the finite difference of this sequence. And the sequence I've drawn here, it's very clearly a different sequence than the one I started with, but in some sense, the bottom one, right, is just shifted by plus 2. I've just added 2 to every case of an n in these three situations. And so in some sense, I already know that my finite difference is just going to be this finite difference, but shifted by 2. It doesn't need to be calculated independently. Since I already know the one, I know the other up to a shift. That's what I say. So I just recognize that my plus 2 situation is the plus 2, and plus 2 version of the original an. So I'm calling it an plus 2. And so then its finite difference is actually the finite difference of a, which I've already calculated up here, but I'm going to evaluate that finite difference at n plus 2, which means I go ahead and swap the first n for an n plus 2 and the second n for an n plus 2. And if I simplify those terms, that's 3 times n plus 2 times n plus 1. So that's the finite difference of my shifted sequence. Before I get too much into the power rule, I do want to mention there's going to be 2 power rules for finite differences. We're going to see that in some ways there's a different version of a power, abstractly construed, that works better for finite differences. We're not going to get there yet, but I just want to put it out there that you're going to see this power rule, you're going to say, wow, that's really ugly, and you're going to want something better. And I'm going to present you with something better. The price you pay is that a power is no longer really a power, it's kind of its own operation. But let's go with the original power rule that I've got here, because this is kind of what you would want to see right away. And what's happening here is we have the finite difference of n to the kth power, right? So you can imagine something like delta n cube equals, whatever you're going to put out there, delta n to the 7th equals dot, 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 whatever you put out there. Let's call it the power rule for derivatives. If I have ddx of x to the 7th, well, the output is what, 7x to the 6th? That's what you get with the power rule for derivatives. Here we would hope to get something similar. And technically we do, and I'll describe how you get something similar in a bit. But you pay the price of a lot of extra terms. We've kind of already seen this with the finite difference so far. Every derivative, every finite difference looks like the derivative plus a bunch of ugly terms. And sometimes it's only a few ugly terms, sometimes it's a lot of ugly terms. Turns out in the power rule, it's a lot of ugly terms. So if I just circled this part of the power rule that I've defined here, that's the exact same as the derivative rule. Let's think back to this binomial coefficient. What is k choose 1? Well, that's like the first non-trivial entry in the kth row of Pascal's triangle. And the kth row always goes 1k and then some other nonsense in it. So this really, can just be thought of as a k, even though I've written it as the binomial coefficient k choose 1. It really is saying, oh, the finite difference of n to the kth power is k times n to the k minus 1. That is the power rule for derivatives right there. We just have to pay this ugly price of everything else sitting over here, which is a bunch of other binomial coefficients and powers of n. So the proof in this case I've actually left as a master exercise because you should be able to get there yourself, even though it's a master exercise, so I won't be assigning it necessarily. You should be able to get there yourself by just thinking about what would this actually mean? N plus 1 to the kth power, and I'm going to subtract n to the kth power. You just go right ahead and use the binomial expansion on n plus 1 to the kth power. What you're going to get is exactly this. That's kind of the point of the binomial theorem. You get exactly this. Oh, but by the way, you get that plus the one term that's missing here, n to the k. But, why is n to the k missing here? It's missing there because I'm subtracting it off over there. And so it just cancels out and you're left with everything except for the very first term of the binomial expansion of n plus 1 to the k. Let's actually look at this. We're going to do an example of quite a few cases of this first power rule. Let's recall really quick how this binomial coefficient works. We've got k choose j is how we call it, and it's defined as k factorial over j factorial times k minus j factorial. And these can be computed by finding the jth entry in the kth row of Pascal's triangle, but they can also just be computed directly, recalling that k factorial is defined by k times k minus 1 times k minus 2 dot 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 times 2 times 1. Or something like 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. You just multiply your way down until you get to 1. Okay, so you can compute these coefficients however you like to compute them. I've got a video on those from the power rule for derivatives section as well. And you're just going to include all of them against the powers, the descending powers of k starting n to the k starting at k minus 1. So let's actually see how we would do this. I'm going to present Pascal's triangle here because these actually help us, come up with all of these entries. So here's Pascal's triangle. This is the 0th row, 1st row, 2nd row, 3rd row, and the 4th row. And then this is kind of considered the 0th entry, the 1st, entry, the second entry, the third entry, and the fourth entry, at least within the fourth row. So you do have to start at zeros for both the kind of the row and the entries. But aside from that, Pascal's triangle gives you all of these binomial coefficients. So let's see if we can do that for the case of delta n cubed. We certainly can. What are we going to do with delta n cubed? We're going to extract the third row's entries, which happen to be 1, 3, 3, 1. And so 3 choose 0 is going to be 1, 3 choose 1 is going to be 3, 3 choose 2 is going to be 3, 3 choose 3 is going to be 1. And then we use descending powers of n when we expand all of these terms. Descend 3, power 3 to 1 and 0. And then, of course, you know, delta n cubed is going to subtract off the very first term, a single case of n cubed. And so that single n cubed is going to cancel right here and right here. What am I left with? I'm left with 3n squared plus 3n plus 1. And that's exactly what I've drawn there. So that's the power rule in the case of n cubed. In the case of n to the fifth, what's the fifth row of Pascal's triangle? Well, I didn't draw it above, but the fifth row ends up being 1, 5, 10, 10, 5, 1. If you decide to complete it yourself, we're looking at descending powers of n, 5, 4, 3, 2, 1, and n to the 0th power here. And we subtract off n to the fifth, so that n to the fifth cancels exactly in the first case. And we're left with 5, n to the fourth, 10, n cubed, 10, n squared, 5n plus 1. That's exactly what I've drawn there. In the case of n to the eighth row of Pascal's triangle, and you should just go through the work of completing this yourself if you want to. It really doesn't take too much time to draw out a lot of terms in Pascal's triangle. Ends up being 1, 8, 28, 56, 70, 56, 28, 8, and 1. And once again, I'm going to take descending powers of n, 8, 7, 6, 5, 4, 3, 2, 1, n to the 0. And then the very first term is the term that cancels, so n to the eighth cancels with n to the eighth, and I'm left with, as my actual computation for delta n to the 8, 8, n to the 7, plus 28, n to the 6, plus 56, n to the 5th, plus 70, n to the 4th, plus 56, n cubed, plus 28, n squared, plus 8, n plus 1. And what do you know? That's what I've got down below. And so at this point, you're probably kind of sick of this first power rule. There's so much extra work that has to go into this power rule. You really don't want to do it anymore. Is there something better? The answer is yes. And I've already hinted at this, but you pay the price of no longer technically working with a power. You work with something else. That something else is called the falling factorial. Sometimes this is called the Pockhammer symbol. And there's also multiple notations for this falling factorial. So sometimes the notation will be parentheses x and then a subscript k, because there's something called the rising factorial as well, which kind of does the opposite. But we're not going to use that notation here. We're going to use the notation x to the power k, but I've gone ahead and underlined that power. So that's kind of the new operation here. And how does it get defined? Well, it's called the falling factorial because what does it do is it produces, what's actually happening here, there should kind of be 3 dots here. What's actually happening here is this contains the first k terms of x factorial, right? So that's why it's called the falling factorial. It really does behave like the factorial. It contains when I'm taking power k, it's the k first terms in the factorial. So something like 7 factorial, we already know is 7 times 6 times 5 times 4 times 3 times 2 times 1, but maybe 7 falling factorial 3, so 3 underlined, is only the first 3 terms. It's 7 times 6 times 5. Okay, something like 7 choose 5 would be 7 times 6 times 5 times 4 times 3. Okay, so it's the first k terms of the factorial. That's why it's called the falling factorial. But it's notated as a power because if we think about this, there is going to be 1, 2, 3, dot, dot, dot. There's going to be k powers of our original variable within this factorial. You kind of happen to have these extra pieces which reduce its size by just a little bit. So that's the falling factorial. And in fact, just like the factorial, when you have a 0th power, you're going to define that to be equal to 1. This is similar to actually the regular power where x to the 0 is also defined to be equal to 1. So here I've got some more examples of the falling factorial for actual integers. 10 cubed, but 10 falling factorial really is going to be 10 minus 0 times 10 minus 1 times 10 minus 2, or 10 times 9 times 8, which happens to be 720. 2 falling factorial 4 is going to be 2 minus 0, 2 minus 1, 2 minus 2, 2 minus 3. And so you'll notice after 3 steps, you do run into a 0, so this just ends up being 0. So really interesting that with falling factorials, if you put that number high enough, it just automatically forces it to be equal to 0. Okay, there's a remark here that basically describes what I was already saying about it generalizing the factorial. I want to move on to the second power rule because that's the whole reason we've defined this falling factorial. The reason we define it is because if we look at the sequence which is n to the k falling factorial k, if we look at the finite difference of that, what do we get? Well, that k comes out front, there it is, and then we just reduce the power by 1. And so this is exactly like the power rule for continuous derivatives. The only problem is that I've had to define a new power. This falling factorial is now playing the role of my power. So a little bit annoying. I'm not going to go through the proof nice and long. As you can see, you can look at the proof, pause it here if you want to see it. It's pretty straightforward, but I'm just not going to go through it for brevity here. Let's look at some examples. So this first one we're going to do, you're going to start to see these sorts of polynomials all the time because they really are falling factorials in disguise, right? We should recognize that as really n squared, right? Because n2 falling factorial is just going to be n times n minus 1. So this is really some version of n squared over 2, but in falling factorial land. So the finite difference of n squared over 2, well, we have our power rule that says when you have the finite difference of n falling factorial squared, you look at that power, you bring it out front, and you subtract 1 from it. When I subtract 1 from 2, I happen to have 1, n falling factorial 1. Something nice to note, if I have falling factorial 1, I'm looking at the first entry in the factorial. That's always going to be n itself. And so we just end up with n here because the 2 that fell out front canceled with the 2 that was in my denominator. I also have a explanation of if we just went ahead and computed this directly using the definition of the finite difference, you do still achieve n as your answer. Looking at a second example of the second power rule for finite differences, we're now just going to write our polynomial using that falling factorial in every setting of the polynomial. And then we just apply linearity of the finite difference to each term here and just treat it as the power rule. Keep in mind the finite difference of a constant still becomes 0. There's my 0. And then I'm going to apply the power rule just like I would for derivatives. I'm looking at the 7, I'm going to bring it out front, subtract 1 from it. I'm looking at the 3, I'm going to bring it out front, subtract 1 from it. I'm looking at the 2, I'm going to bring it out front, subtract 1 from it. And as I already mentioned, the 3 becomes a 0. And so now we just write our results in terms of the falling factorials. I have negative 7, n to the falling factorial 6, plus 6, n to the falling factorial 2, minus 8. I could write it as n to the falling factorial 1, right? That's what 2 minus 1 falling factorial is. But we already know that n, 1 falling factorial is the first entry in the factorial, which is just going to be n. That's a nice second example. We also have an exponential rule for finite differences. This one's extremely straightforward to prove. So I'm actually going to jump into the proof first. If I just write out the finite difference of an exponential sequence, I'm going to add 1 to the sequence, and then I'm going to subtract the sequence without adding 1 to it. And if I just use an exponent rule, well, what do I have here? I have 1 extra copy of a minus a 1. So there I can write it as a minus 1 times a to the n, which means the finite difference of a to the n is a minus 1 a to the n. In particular, that makes, back in derivative world or continuous derivative world, we had e to the x being the function that was invariant under a derivative, right? Invariant or unchanged. In finite difference land or sequence land, it turns out to be the exponential of base 2. So this base e is really special to a continuous world, where the base 2 is actually special to a discrete world. So that's the exponential that's left invariant under the finite difference. A couple nice examples of this exponential rule for finite differences. Of course, if I take base 10 and I jump back up to what does the rule say? The rule just says take your base and subtract 1 from it. That's the new coefficient you get. The rest of the powers remain. And so here I'm taking the finite difference of 10. I'm going to end up with 10 minus 1, which is 9. And then the rest of the powers remain. So 9 times 10 to the nth power. I could do something with negative 1 even. So let's think about the sequence. This is the alternating sign sequence, remember? So we have 1, negative 1, 1, negative 1, dot, dot, dot. What is the finite difference? What is the difference between these two values? Well, that difference is negative 2, but then the difference between negative 1 and 1 is positive 2, and then the difference between 1 and negative 1 is negative 2 again. So when you think about it conceptually, it should always have a magnitude of negative 2, but kind of the sign is always alternating. There you go, negative 1 to the n. But that was just me thinking about it conceptually. This also comes directly from our rule, right? Because if our rule is delta a to the n equals a minus 1, a to the n, and I replace a with negative 1, this is saying delta negative 1 to the n is, well, negative 1 minus 1 happens to be negative 2 times negative 1 to the n. And so it totally aligns with what we're thinking conceptually, but it's also a very slick rule we can apply to this finite difference. We do also have a logarithm rule for the finite difference, a little bit more mundane. The logarithm rule, you just kind of write it out. I'll go back to the proof again. You write it out. By definition, we're going to shift forward by 1, and we're going to subtract the original sequence. Well, log rules say, hey, if I've got a subtraction between logs, that can be written as a division within logs. And if I simplify that division a little bit, I just end up with 1 plus 1 over n on the inside of my logarithm. So that's going to be true independent of the base of the logarithm, because bases don't care about log rules very much. Independent of the base, this is always going to be the finite difference of the logarithm. And so here I've got some examples where maybe I want to take the finite difference of log of n squared. And if I want to make my life a little bit easier, I can recognize that, okay, I don't really have a chain rule, so I can't do derivative of the outside multiplied by the derivative of the inside. What I can do instead is I can look at that square and use a log rule to pull this square out front. That's why I'm writing it as 2 log n. And then I can use linearity of the finite difference to pull the difference through and call it 2 times the difference of log n. And that's going to let me use now my log rule, which just happens to be, I'm going to replace log of n with log of 1 plus 1 over n. So I'm replacing this finite difference log n with log of 1 plus 1 over n. Here's a case where I've got logs with 2 separate bases, and I've multiplied them by a 2 and a 3 and subtracted them. Well, I'm going to use linearity of the finite difference again to distribute the difference to both terms, and this log just becomes log base 10 of 1 plus 1 over n, and the second log base 2 becomes log base 2 of 1 plus 1 over n. Okay, then we're going to finish out with something that's maybe a little bit too complicated for anything that you would actually be asked to compute or show your proficiency with, but just gives a good example of kind of the breadth of knowledge we have or have accounted for so far in finite differences and rules for finite differences. So suppose I've got this overly complicated sequence here, which is defined by 2 log base 7 of n to the following factorial 5 plus 1 times e to the nq minus 1 minus n following factorial 2. It turns out we will be able to use a lot of the rules we've developed in this chapter to compute and simplify it to a certain extent the finite difference of this large term. So what are those rules going to be? Well, we definitely have a product rule because there's a product sitting right there, and I've notated that trying to use color coding here as well. So there's a product sitting around there. There could be a chain rule, right? But I do often say that I reserve the chain rule for the appendix, and we're actually not going to apply it in this example either. But where does the chain rule show up? Give you some practice to maybe recognize these for regular derivatives. It's going to show up right here where we've got a log base 7 on the outside and an n to the 5th on the inside, n to the following factorial 5 on the inside. And it's also going to show up here with an exponential to a specific power nq minus 1, right? So there's really a nesting of sequences happening there, a nesting of functions happening there. We also have a case of the first power rule showing up, and that's specifically in the power of the exponent, so nq minus 1, so it's a regular n cube, not n following factorial cube. And then we also happen to have a second power rule showing up in a few places. I've got a following factorial there and a following factorial there, so 2 places of the second power rule showing up. Okay, so we're going to compute the finite difference of this basically in the order of the rules that I showed above, which means we're going to start with the product rule, right? So we're going to take the finite difference of the product of those 2 sequences. And if we remember our product rule well, it says you take the finite difference of the first sequence, keep the second one the same, add the first sequence, and then multiply by the finite difference of the second sequence. And if we were in continuous derivative land, we would be done, right? This finishes the product rule. But in finite differences, we end up having to multiply the finite difference of both sequences together and add that term to the end as well. So to that end, really the terms that matter here for us to kind of finish this off is we're going to have to explicitly calculate this piece, which is the finite difference of kind of the left-hand side, and we're going to have to explicitly calculate this piece, which is the finite difference of the right-hand side, and of course, include those 2 terms at the end here as well. So once we compute those 2 individually, we should be able to combine it all together into this product rule. To that end, we'll look at the first one, and we'll jump down here where we could use the chain rule, right? And we have the appendix that has the chain rule for us. We really don't want to. I would say try not to use the chain rule. It's cool that it exists, but it's just so unwieldy that we really don't want to use it. So we're just going to calculate this directly. Let's remember what it means to compute a finite difference. Well, we're going to take this n, and we're going to swap it out for an n plus 1, and then we're going to subtract the original sequence where we did not swap it out for an n plus 1. And if we do that, actually quite a few things work out for us because, yeah, this plus 1, we have minus plus 1 there, so those plus 1s cancel. And then we've got some 2's, 2 minus 2, so the 2 can just factor out to the left. And then log rules, I've got a log base 7 minus a log base 7. So log rules say, hey, you can actually divide on the inside of a log if you're subtracting on the outside of a log. And at this point, this looks like maybe it is pretty hard to actually simplify. But if we write out what they mean, it turns out they simplified okay, right? Because these really are factorials. They're falling factorials, or think about it like powers, right? Falling factorials or powers, you can write these out explicitly. The first 5 terms of n plus 1 factorial is going to be n plus 1, n minus 0, n minus 1, n minus 2, and n minus 3. And then the first 5 terms of n factorial would be n minus 0, n minus 1, n minus 2, n minus 3, and n minus 4. Well, it turns out that, yeah, we've got a lot of terms, n minus 0 canceling from both, n minus 1 canceling from both, n minus 2 canceling from both, and n minus 3 canceling from both. We're just left with an n plus 1 in the numerator and an n minus 4 in the denominator. So that does simplify actually quite a bit, which is useful. And then we can look at this second finite difference that we still have to calculate, and we'll go through that. Also could use the chain rule, but we won't, and we'll just calculate directly. How is a finite difference calculated directly? Well, you take n and you swap it out for n plus 1, and then you subtract the original sequence, then we're going to simplify from there. So if I want to expand something like n plus 1 cubed, we're going to use our lovely Pascal's triangle, where the third row is 1, 3, 3, 1, and expand out n plus 1 cubed. That's going to let me simplify that power, e to the n plus 1 cubed, a little bit, and rewrite it as n cubed plus 3n squared plus 3n, and then we're going to be subtracting e to the n cubed minus 1, which in fact can factor out of both terms, and what we're left with is e to the 3n squared plus 3n plus 1 minus 1 times e to the n cubed minus 1. But at this point, that just calculates the first of the two terms in this piece that was left over still. If we want to calculate the finite difference of the very last term, n to the falling factorial 2, well, we do have our second power rule for that, right? The second power rule says, grab that 2, pull it out front, there it is, and we're going to reduce that power by 1. So that's really 1 falling factorial, which happens to be just n to the first power still. And so here, if I include this as that calculation, will be the finite difference of the second term. And then if I jump all the way back up to this product rule, I can, since I've computed that already, that was kind of this 2 log 7, n plus 1 over n minus 4, and then I just went ahead and computed these two terms as well. I'm going to shove all of those in, and I end up with this horrendous piece of mathematics here, which describes the full collection of rules that I can potentially apply here, and this is what the finite difference is. And you kind of get an idea here where it would probably just be easier to write, you know, the finite difference of this out explicitly, which would just be 2 log base 7 of n plus 1 to the falling factorial 5 plus 1 times e to the n plus 1 cubed minus 1 minus n plus 1 falling factorial 2 minus the whole thing without me putting some n plus 1s in there, 2 log base 7 n to the falling factorial 5 plus 1 times e to the n cubed minus 1 minus n to the falling factorial 2. You could have, from the beginning, simply written the finite difference like this, and it is, you know, totally computed, totally correct. We didn't really have to use our rules. So I do want to stress that rules are nice to have. They're not actually useful for finite differences. We're going to see them useful in the next 2 sections, I promise. But, you know, for now, it's going to feel like, why in the world did we even do this? A little bit of motivation. Math is just a game. You try to make crazy statements. We've made some crazy statements. It's fun. But the other thing is that these do have some use in trying to undo finite differences. If you can recognize these rules in reverse, it can actually be useful. Anyway, I'm going to finish off. I know it's been a long one today. I'm going to finish off by mentioning I did combine all of the rules into a lovely table, just like I did for derivatives, but these are the finite difference rules. We've got some funky notations here. These are the Greek letters, capital sigma. We're going to cover what these letters mean in the next section. So even though you haven't studied them yet, you might not know what they mean. Give yourself a section and we're going to figure out what those mean. Anyway, thanks for hanging in there. I'll see you in the next one. Bye.